Good morning, everybody. It's exciting to be here. I've had such good experiences in past years with Jerusalem Summer School. It's great to be here again, meet some of the future stars of economics, if history is any indication, as well as some of the existing stars of economics. So my topic today is matching with contracts. Is Eric here, by the way? Eric's not here, so I won't. I was going to comment. I wanted to be fair to Eric that I'm going to take a different perspective than the one that he opened with. Eric Maskin was trying, as I will try to do, to connect what goes on in matching theory to the main corpus of economics. And I was also curious about the connections, but I don't think that connecting it to competitive equilibrium and Brouwer's fixed point theorem and that way of approaching prices is the main thing one wants to do. It's not the most fruitful way to approach it. And I'm going to show you a different approach. So the idea of matching with contracts is to nest, first of all, to nest various matching models and auction models, including the Vickrey auction, and some competitive equilibrium models too, some with and without money terms and with and without other contract terms. Trying to understand how does this fit in with the whole corpus of economic theory. And I want to think about the Gale-Shapley algorithm as a planning algorithm. And I want to fit that into the corpus of economic theory too. So it's related to Walrasian price adjustments, which you all know is a mechanism in which if you take goods that are in excess demand and you raise their price, and goods that are, if they're in excess demand, you raise their price. If they're in excess supply, you lower the price, and you sort of hope that converges. And we've known ever since, I don't know if Ken's here either, since Arrow and Hurwitz, that if you have gross substitutes, that kind of process converges to an equilibrium. So what does that have to do with all of this? And then I want to connect it to Marshallian quantity adjustments. So when I talk to you guys tomorrow about what's the most exciting design going on the auction side of market design, the design of the U.S. incentive auction, which is enormous and complicated, and you'll hear all about tomorrow. It takes advantage of a different kind of dynamic adjustment process, Marshallian dynamics, and which is another classical idea in economics, and I want to bring that into the frame too. And then a different class of algorithms called cumulative offer algorithms, which are part of the basis, eventually became part of the basis of the spectrum auctions that are widely used in Europe. And you'll see how those work as well. So the mathematical connections are particularly tight among models that satisfy some general substitutes condition. And I want to show you what that is and then derive the whole theory in some general way and get some concept going of how all of this is part of a whole. Okay, hi Eric. You missed my comment about your talk, its relation to my talk, but I'll tell you later. Okay. This lecture is based mainly on work that I did with John Hatfield, published in 2005, which is part of enormous literature on matching theory, which I won't try to summarize here. But it's also connected to, especially closely connected to Kelso and Crawford, who a long time ago introduced prices into the matching model. And it's funny how long it took for that to catch on as being really a central part of matching theory, but it is, and it extends matching theory to the presence of prices. It's also connected to some work on auction theory that Larry Ausubel and I did for problems that don't have the substitute structure, and I'll show you cumulative offer processes, and I'll show you how that relates and how Vickrey auctions relate to. It's going to turn out that the Vickrey incentive compatibility theorem and the Gale-Shapley incentive compatibility theorem on a shared domain are the same theorem. So we're trying to draw connections and pull this into a unified framework. So here's the contract environment. Here's what we're going to be studying. So it's going to be characterized by three finite sets, which I will call doctors, hospitals, and terms. And doctors, just some finite set. It could represent. Doesn't have to be doctors. Obviously, it could represent anybody. The hospitals. These are just heuristic. F is going to be the set of market participants. It's the union of the set of doctors and hospitals. And T is the set of terms, which in addition to wages could be location, hours. And the recent comprehensive exam we had at Stanford for our micro students, the exam problem said, go back and do the Gale-Shapley marriage problem, but suppose that the man, when proposes to the woman can say, let's elope and go to Reno, and we'll come back and I'll work at Facebook and you can be a graduate student. And the terms can matter, right, as part of the point. So you can do so I want to do Gale Shapley with general terms. So that'll be what terms is. And a contract then is going to be an element of the set D cross H cross T. It's going to have on it 3 blanks. There's going to be sort of some standard form contract. In one blank, you write down the name of the doctor. Another blank, you write down the name of the hospital, with all the standard terms. And then there's, other blanks in which you can write down these additional terms. And that's what a contract is. Okay? The market participants' preferences are encapsulated in choice functions. So each market participant has some choices that he'd make. And so, for example, a doctor, given a set of contracts Y, is going to choose, typically we're going to be looking at doctors choosing singletons, but more generally, the doctor could be choosing many contracts. So he chooses some set of contracts that have his name on it. So X sub D with the capital D means that this is what's on the blank, on the doctor blank in the contract. So it's this is Dr. Maskin here, okay? And a doctor chooses among contracts bearing her name, and a hospital chooses among contracts that are bearing its name. So the choice that the hospital makes from a set of contracts is some subset of the set of contracts that bears that hospital's name. So when we look at the market, there's some set of contracts that are available out there, and those are the preferences that we see. And associated, we're going to assume that there's an associated preference relation that rationalizes these. And from the market as the whole, the doctors' and hospitals' choices, and what I'm going to refer to as their budget set sometime, are just the union of these things. So the contracts that ended up being picked by all the doctors collectively is just the union over the set of doctors of the contracts that are picked by the doctors individually. And similarly for the hospitals. So those are going to be what choices are made if you if some big set of contracts is available to you in the market.
Can the terms include statements about other doctors or other hospitals?
No. So the
Singular couples, probably.
no, it's not going to mean. So I'm going to emphasize for the first part of this the substitutes case. That's going to unify a big. So you also missed a reference to your paper when I was here. I mentioned Arrow Hurwitz and the convergence. Well, I'll talk to you about that after too. You guys should learn to show up on time, by the way. Okay. So I'm going to talk about. I'm going to start by talking about substitutes, and this is the frame in which many of these things come together. So we'll find that a lot of things are the same in worlds with substitutes. But I have to tell you what substitutes means generally. So we want to define the concept of substitution to be universal, so that the relation that x and y are substitutes doesn't depend on the presence of that there are other alternatives. So normally in price theory, if you were studying consumer theory and economics, whether an increase in the price of good X caused an increase in the demand for good Y might depend on the price of good Z. Okay, these are, but those kinds of substitutes we're looking at here are more like the gross substitutes of Arrow Hurwitz, where the relationship is universal. We say that X and Y are substitutes if an increase in the price of X doesn't reduce the demand for Y, and independently of all the other prices. Okay, so we want a universal concept, and we want to characterize a situation in which every contract is a substitute for every other contract, like the women regard the men, every man is a substitute for every other man, or in Arrow Hurwitz, every good is a substitute for every other good. And so here is the general definition. Contracts are substitutes if for any two contracts in the set of all contracts and any subset of contracts, Z that's included in X, if X is not chosen when it's available together with the other elements of Z, then it also won't be chosen when it and Y are available with the other elements of Z. Okay, this is the same kind of definition that Al gave for doctors being substitutes for hospitals. It means, there's an absence of complementarity. If you were to choose X in this case but not that case, that would mean that, gee, when you're optimizing, oh, Y's available. Well, these guys go well together. If I'm going to take Y, then I want to take X. But if you weren't going to take Y anyway, and you weren't taking X over here, then you won't take X over there. So if this were chosen, that would be some sense that in which x and y were complements. I can't.
So you're not considering couples?
I'm not here considering couples. I'm going to turn toward the end of the lecture. I'm going to come back. But the object of this lecture is to bring together the things, most of this lecture, to bring together the things that can be brought together. And they can be brought together under the context of substitutes. Toward the end, I'll say a few words about other things too. But that's not where I'm starting. So more succinctly, the way I want to think about this is in terms of the rejection function. It turns out, you heard the word lattice a couple of times. Nobody's defined for you what a lattice is or what the big theorems about lattices are. The lattice structure, the order structure, is what connects everything here. It's the idea that certain functions are increasing, that certain sets, well, you'll see exactly what it is. But here, the first function that's increasing that I'm going to begin with that will structure everything for you is the rejection function. What it means for goods to be substitutes is that this function is what we call isotone, which means that non-decreasing, essentially. That if you have a bigger set to choose from, then you reject more things. Okay, this is the same definition as that. It says that a certain function is in non-decreasing, more precisely isotone is the correct technical term, that from a larger set of things, if I used to reject it before, I still reject it, and I might reject some other things when you make the set bigger. Okay, that's going to be our general notion of substitutes. So part of the point is that this embeds traditional matching models. So if you take T to be the set of wages, a finite set of wages, and you have the Kelso-Crawford model here. If you take T to be a singleton, so there's not really anything to fill in the blank that says terms, then you can identify the set of contracts with D cross H and get the Gale-Shapley algorithm. And contracts are substitutes in the Gale-Shapley model if and only if they're substitutable in the sense of Roth and Sotomayor. And contracts are substitutes in the Kelso-Crawford model if and only if they're price-theoretic row substitutes, which means the key idea, the way you see that, and here's the key step, is that if you raise a worker's wage, think of the wage, so if I'm a firm, think of the wage as being the amount that I have to pay to, I want to hire Ken. The wage is the minimum amount that I have to pay him. But I could hire him for more money, too, if I wanted. He'd say yes to that as well. So in that case, raising the wage means reducing the set of options that are available to me. I used to be able to hire him for 100 or more. Now I can only hire him for 110 or more. It reduces the set of options. And to say that things are substitutes is to say that when the wage goes up, I reject more contracts. That's identical to the price-theoretic definition of substitutes. Okay? The concept here is that the prices are used to identify the firm's choice set, just as they do in standard economics. So what are some examples of substitutes? Responsive preferences. By the way, I've always wondered why these preferences were called responsive. The usual theorem in economics when we do this in choice theory is additively separable. Preferences are responsive in matching theory if and only if there exists increasing a function, basically, of the individual doctors such that my utility from any set is the sum of the utilities of the individuals over my feasible set, which has a limit on how many doctors I can hire. So they're additively separable preferences, and those are what are called responsive. Those are substitutable. You could have separate openings for men and women. Men and women would still be substitutes, although only in the weak sense. That is, if an extra woman became available, it wouldn't affect your choices of men at all if you had separate positions. And for women, if you had an extra woman available, then you would reject all the women you were rejecting before and maybe somebody else. The hospital openings with reversion, which from the National Resident Matching Program, where you have two kinds of positions. If you have a more specialized residency and you have general medicine or internal medicine residency, and if you can't fill but you want a certain number of residents in your hospital, and if you can't fill the specialized position, then you then you start making offers on the less specialized position. Those are substitutes preferences. Suppose I have a hockey team that regards players as substitutes in the draft. It's drafting players. It needs a goalie, a defenseman, and a forward. The players all have different skills, so some players might be able to play any of these positions. Might be able to play more than one position. And suppose the team's playoff is the sum of the values of the players in the positions to which they're assigned. So some players may be specialized and only able to play one position. Other players may be able to play multiple positions. The team can assign any of its players to any position. Players are substitutes. Okay, it's just routine to verify these things. So substitutes encompasses a lot of different possibilities. Although it's very restrictive, but it does encompass a lot of possibilities. Okay, now there's a dual characterization of substitutes that's also very interesting in making these connections. That comes from the indirect profit function of the firm. So let W be a vector of wages in the classical theory of the firm. We can speak of its indirect profit function. This is a standard concept in economics, and those of you who are not from economics, this is also known as the Fenchel dual, and it has other names too. I'm not sure what name you would know it under, but the idea is that you pick from out of your feasible set the thing that maximizes your profits when you have to pay a wage of W per unit. Okay, that's this thing is the dual function for the function, the Fenchel dual of the function f, and it's also the indirect profit function of the firm in price theory for those of you who have come from that background. And there's a lemma in economics called Hotelling's lemma. This is, for some of you, this is the envelope theorem in other parts of, from other technical backgrounds, that says that for almost all wage vectors, and in fact for every point of differentiability of this function, the firm's demand for workers is just the negative, well, the firm's demand for worker I at these prices is the negative of the partial derivative of the function pi with respect to the price of good I. And this is, in general, its demand is just minus the derivative. This is the envelope theorem in optimization theory, and it's Hotelling's lemma in economics. Okay? All right. So in the theory of the firm, workers are substitutes if and only if pi is a submodular function. So roughly speaking, a submodular function, when you're speaking about functions of real numbers, is if the function is differentiable, it's a function whose mixed partial derivatives are non-positive. And to be substitutes means that if I want to look at the demand for worker I and I increase the wage of worker J, what's going to happen? Well, the wage of worker, the demand for worker I has to be increasing in the wage of worker J. So that means this mixed partial derivative in the smooth case would need to be non-positive. The differential intuition you can use for everything. All of these things have extensions to the discrete case. So there's no problem of thinking about it, if you like, in the differentiable case. Okay, so submodularity of the dual function is the same thing as the substitutes condition. That lets us connect big parts of price theory to matching theory. Okay, and here's a theorem of Hatfield and commoners. The indirect utility function in the general case, so you can say that represents preferences or choices. Say it represents preferences or choices if whenever the utility of a set of choices y is bigger than the utility of a set of choices z, that happens only if the choice that you would make from the set y is something you prefer to the choice you would make from the set z. Okay, so this is like an indirect utility function, but it's now expressed without using prices. Prices describe your choice set, and here the sets describe your choice set. And the indirect utility is higher in one case in exactly the same. It represents preferences in exactly the same kind of way that it does in the classical theory of the firm. We say U is submodular if for all contracts X and all sets of choices Y and Z that are a subset of the set of all contracts. X, remember, is the set of all contracts. If the incremental utility that you get by adding X to your choice set is bigger than the incremental utility you get by adding X to the larger choice set. So we're saying that, that when you add x to a choice set, that's a choice you might want to make. It might increase your utility. It'll increase your utility more if you've started with a set that is less inclusive rather than a set that's more inclusive. And the theorem is that contracts are substitutes for a participant if and only if the preferences can be represented by a submodular utility function. So that's the analog in the general theory of the statement that I made for you in price theory. So you can start to see that we're trying to integrate and express in familiar price theoretic terms the very same concepts that you've seen that are familiar to economics from a price theory point of view. Okay, and I have a proof here, which I don't think I'll go over because I'm running late already. But it's pretty straightforward, and we will make the slides available, is that right? Okay, so we'll make the slides available, so I won't belabor the proof for you. Okay, so that's background. Those are the generalizations of the concepts, and now let's go to what stability means. So I'm going to say that a set of contracts is stable if it satisfies two conditions: individual rationality, which means given the set of contracts, the firm, each firm or each participant is selecting exactly the contracts that have its name on it. So I got a set of contracts, and I said this is a stable allocation. Here it is. I've got a stack somewhere, and Ken sorts through the stack and says, this one, and this one are mine, and says, yep, given those choices, those are the ones I want. I'll take them all. Okay, so that's individual rationality. And the set also has to be unblocked, so there has to be no other set of contracts Z such that if Z has to have some things in it that weren't already in Y. Okay, so no other set of contracts Z that includes things that weren't in Y, such that for all the participants, they would take these contracts if they were given them in addition to the contracts that are in Y. So you take this set of contracts there. Here's a stack of contracts that Ken's looking at, and all of a sudden there's some other contract in there that has Eric's name on it, and Ken says, gee, oh yeah, I'd like that contract too. It's got Eric on it. And Eric is also saying, gee, I'd like that contract, given that I have the other options I have, and also the possibility of working for Ken here in Jerusalem. Okay, so so that's what it means to be. There are no blocking coalition. Means there's no set of contracts that includes some new contract, such that everybody would take those contracts when faced with those plus the contracts that are already offered to them. Okay? Clear that generalizes the notion of... Okay, our next task is to characterize stability in terms of agents making optimal choices from a budget set, and those sets being mutually consistent. And then we're going to look at an algorithm to find stable allocations and characterize it as both related to the Gale-Shapley algorithm and to other algorithms, including Marshallian dynamics and Walrasian dynamics and cumulative offers and other things. Okay, so this, by the way, is what Marshallian dynamics is. I'm going to do this again tomorrow, so I wonder if I should do this today. But for those of you who've forgotten what Marshallian dynamics is, or never knew, the notion is that one way to try to find an equilibrium, so here I imagine there's a supply curve somewhere and there's a demand curve somewhere, and you end up, you start by setting a quantity, and you find out what the prices are, the supply price and the demand price, and you discover if markets don't clear because the supply price is higher than the demand price, then you reduce the quantity and continue. And if you still haven't cleared, you reduce the quantity and continue. Okay, so this is an algorithm, a quantity adjustment algorithm for finding equilibrium. We'll see that this becomes tomorrow. I'll show you this becomes part of the basis of the U.S. incentive auction that we're planning for buying and selling radio spectrum. But I'll tell you more about that tomorrow. Okay, oops, what just happened? There we go. Okay, so substitutes and stability. So if contracts are substitutes, did I miss a slide? Here it is. Here we go, okay. So here's what deferred acceptance now looks like. Okay, informally, I'm going to have an algorithm, and informally, the state of the algorithm at any time, I want you to think of as consisting of two sets. These are the sets of offers that the doctors think are available to them, and the sets of possibilities that the hospitals think are available to them. Okay? These are going to be their budget sets, roughly. They represent contracting opportunities as seen from the two different perspectives. Formally, we're going to just require this be a set of contracts. It's a subset of the set of all contracts. And the hospitals have some set of contracts in mind, a subset of the set of all contracts. And as the algorithms progress, the doctor's budget set is going to consist of all those contracts that the hospitals haven't rejected, and symmetrically for the hospital. So here's how it's going to look. You're going to imagine during the course, so this is going to be a fixed point operator that we're going to be looking at here. And it's going to look as follows. What the doctors are looking at is a set of offers that depends on what the hospitals are looking at. So these are the offers that the hospitals have not rejected. So the hospitals, if they're facing a set of contracts H, have rejected RH of XH, and X minus RH of XH is just the complement. It's the set of contracts that have not been rejected, and that's the new set for the doctors. And similarly, the set of contracts that the hospitals are looking at depends on what the doctors are looking at, and it's everything that the doctors haven't rejected. And my function is going to take the a set from the hospital and the set from the doctors and generate a new set for the hospital, another set for the doctors, and that's it. Okay? I claim this is the Gale-Shapley algorithm. So here's how it works. First of all, the fixed point argument. If contracts are substitutes for all market participants, then a collection of contracts is stable if and only if there's a fixed point such that A is the intersection of XD and XH. So this is a budget set characterization. It says, you know, there's a trade taking place, and there's some set of trades that's in Ken's budget, he can afford it, and it's in Eric's budget, he can afford it. And this is the set that both of them can afford, and they're trading it. Okay, so these are going to be thought of as the budget sets of the doctors and hospitals, and the intersection of them are things that neither of them reject, which means it's the trade they make. Okay, and so what we're going to be looking at is, so we think of these again as budget sets. The hospitals have rejected some contracts. The doctors think of everything else as being available. The doctors are rejecting some contracts. The hospitals think of everything else as being available. And notice that that if you take the union of these two things, you get the set of all contracts. Okay, everything that's not rejected by somebody is in both of these sets. Okay. And so, oops, what is going on here? Having trouble with my control. Here's a proof sketch that just shows you how the argument works. Suppose that I have something that's in the intersection of these two sets. Well, any of a fixed point, okay? Any individually unacceptable contract has already been rejected. So clearly, you know, there's nothing going to be in here that's unacceptable to the doctors because they're rejecting everything out of their feasible set that's unacceptable. So there's no unacceptable contract is in A. And by construction, if there's a contract that's not in any individual contract that's not in the intersection, if it were proposed, it would be rejected by one party or the others. That's how we've constructed these sets. If it were proposed, it would be rejected. So we don't have a blocking coalition that consists of a single doctor and hospital making a deviation. And by the substitutes condition, if there were multiple additional contracts were proposed, they'd still be rejected because the rejection functions are isotone. As I add more contracts, I never stop rejecting things that I was rejecting before. So consequently, there can't be, if A is the intersection of XD and XH, which is a fixed point, then the intersection is a set of stable allocations. And conversely, if A is stable, we can construct budget sets that support it in the following way. Every contract that's not in A would, if it were proposed, be rejected by either the hospital or the doctor. So you just sort it. And if it would have been rejected by the hospital, you add it to XH. And if it would have been rejected by a doctor, you add it to XD. And you take all the contracts that are not in A and put them in either XA or XD. And you now have a set of XA and XD that's a fixed point of this operator. And that supports the stable allocation. So the stable allocation just arises as, from a budget set, a generalized budget set. Okay? Realize it's a little more abstract than what we were doing before because it's we're trying to unify things, but this is exactly the same thing that goes on in the Gale-Shapley algorithm. And what's more, what's more is that what the mathematics that handles this generally, and I realize I have to do an aside because there's such a varied background in the group, so I have to take a moment to do just a little bit of lattice theory. Lattice theory is basically the mathematics about how bounded sequences converge. You know, we all know that if you have a sequence of real numbers that's, let's say, positive real numbers that say that's decreasing, it converges to a limit. And if it's integers or any finite set, and we have a decreasing positive sequence, it eventually achieves that limit, right? So those facts are not just true about the real line; they're true about a much bigger class of ordered sets, and that's what lattice theory is about. It's about the biggest class of sets for which these things are true. And we're just going to see how that mathematics unifies all these things we've been speaking of. So here is just a couple of slides on lattices in order. So we're going to start with a set X, and we're going to start with a relationship on it that's transitive and reflexive. And a pair X with an order is a lattice if for all two elements X and Y and X, the greatest lower bound and the least upper bound both exist in that set. So if I have, you know, a set of 2 points, let's say, in the plane that's just 0, 1, and 1, 0, ordered in the usual component-wise way, that's not a lattice because there's no lower bound for that in the set. In particular, there's no greatest lower bound in the set. So a lattice you have to be able to find a greatest lower bound for any pair of points, and you have to be able to find a least upper bound for any pair of points. So and we're going to call that the greatest lower bound the infimum, denoted by this meet symbol, and we're going to call the least upper bound the join here. So let's take a look at some examples. Suppose that X is a class of subsets of some finite set, and suppose that X less than or equal to Y means that X is a subset of Y. Okay? Well then, being the meet just means being the intersection. Why is that? If I have two sets, what are the sets that are smaller than that set? That's all the subsets. If I've got X and Y and there are two sets, what is the biggest set that's a subset of both of them? It's the intersection. Okay? If I want to find the least upper bound, I've got two sets, X and Y. The bigger sets are sets that are supersets. What's the smallest set that's a superset of both? It's the union. So that's an example of a lattice. Here's another example of a lattice. These are the two examples we'll use, where X is just the n-dimensional Euclidean space, and X greater than or equal to Y means that it's weakly larger in every component. Then we'll say that the meet of X and Y is the point in Rn whose ith component is the component-wise minimum. So if we had our 1, 0, and 0, 1, the meet would be 0, 0. And the join would be 1, 1, the component-wise minimum and the component-wise maximum. Okay? This is an example of a product lattice, which we will also need as we go forward. Okay, and the big theorem I'm going to use that connects the parts of these things that I've been trying to connect from the beginning. And by the way, so this is one of the places where my approach differed from what you were doing earlier, Eric, when you were trying to unify things through convexity and Brouwer's theorem. I'm going to try to unify them instead through Tarski's theorem. So we've approached this problem in different ways. So I'm going to say that this is a standard definition, that a lattice is complete if not just every pair of elements has a least upper bound and greatest lower bound, but every set. So this is sort of like compactness. I'm going to want bounded sequences to converge. And in order for them to converge, I'm going to want to be able to take a whole sequence or whole set of items and be able to find its least upper bound or greatest lower bound. So that's what we mean by complete. Roughly, this just means that bounded monotone sequences have their limits in the set. And I'm going to say a function is isotone if whenever x is bigger than y, f of x is bigger than f of y. Okay? And here's Tarski's theorem. if you have a complete lattice and an isotone function from the lattice into itself, then the set of fixed points is a non-empty lattice. So there is a fixed point, and the fixed point itself is a lattice. Okay? In particular, it has a largest element and a smallest element. This should start to sound like the medical match, right? That's the structure that's in the medical match I'm going to show you is just an order structure. Moreover, if this set is finite, that has a largest element x max and a smallest element x min, then the sequences in which you start at the top with x max and you iteratively apply this function, or when you start at the bottom and you iteratively apply the function, they converge in finitely many steps to the largest and smallest fixed points, respectively. Sounds a lot like the Gale-Shapley algorithm. It is the Gale-Shapley algorithm, so here's how it comes up in matching. I'm going to start with the points I'm looking at, sets of doctors and hospitals. I'm going to say that x is bigger than y if it's worse for the doctors and better for the hospitals. That is, if there's a smaller set, if xd is a subset of yd, so the doctors would obviously like to be choosing from a bigger set, and yh is a subset of xh, so the hospitals would obviously prefer to be choosing from xh. So this is an order on the set of budget sets. Hello? Not sure why I'm not getting, there we go. Okay, with this definition, higher pairs represent expanded opportunities for hospitals and contracted opportunities for doctors. And I think my battery must be running out. I better step over here. Okay, the domain of the function f described earlier is a finite lattice. Meets and joins represent the intersections and unions with respect to these orders, just as I've shown you. So it represents unions and intersections with respect to the first component and intersections and unions with respect to the second component. Okay, so we have a lattice. And the operator f is isotone. I'm going to go back and show you the operator f again so you can see that it's isotone. Where's the operator f? Here's f. So when goods are substitutes if and only if RH is isotone. That was essentially our definition of substitutes. So what happens is that when I get a bigger set of doctors, I reject, the hospital rejects a bigger set. When I get a bigger set of contracts for the hospitals, they reject a bigger set. That gives me a smaller set for the doctors. When I get a smaller set for the doctors, they reject fewer contracts. That gives me a bigger set for the hospitals. So this whole function is isotone in the order that I've just described. So the set of fixed points of the function f is non-empty, and it has a maximal element, and it has a minimal element. And if you iterate applications of f starting from the highest or the lowest point, it converges down or up to the extremal fixed point. So what does this mean? If we start from the point, suppose we start from the point where the doctor's set xd is just the whole set of contracts x, and the hospital set is the empty set. That's the highest point in the lattice from the doctor's point of view. It's the complete set of the whole set of all contracts. So the doctors think everything is available, and the hospitals think, gee, I don't have any offers at all yet, right? And then the algorithm begins, and the doctors say, well, if everything's available, I'm going to reject all of these. Here's what I'm going to choose, and I'm going to offer that to the hospitals. And the hospitals say, great, we have some offers now, but I'm going to reject some of them. And so we get a new set for the hospitals that's bigger than it was before. And when we iterate, we'll get a new set for the doctors. Doctors think, oh, gee, not all the contracts are available. Some smaller sets available. I'm going to iterate again. And the doctors are going to face, through the algorithm, a decreasing budget set. That is, there's fewer and fewer contracts that are feasible for them. The hospitals are going to be facing more and more contracts that are feasible for them. And this is an isotone function. We're going to get a sequence that converges monotonically down to the largest fixed point. That is, to the largest stable allocation. And if we start from the bottom, similarly. Okay? Yeah?
The So the classical Gale-Shapley and the classical,
Mhm.
let's call them classical applications, yields an efficient algorithm. Is that an analysis, if you go over to Tarski in this very general
This is the
setting,
same algorithm.
in the same cases,
Yes, you're right.
but in the very general setting,
Ah,
can you say, or is there an analysis when efficient algorithms exist beyond the existence theorem, or the fixed point? And
so
then
so I don't know any theorems about the efficiency of this. It is a monotonic algorithm, so it's pretty fast. But I don't know any theorem that speaks to its efficiency compared to other algorithms. Let me push on. Yep.
I think it may be something like O of number of contracts squared or something like that.
Okay.
Most each contract has to be proposed once or something given the monotonicity structure.
Yeah. Yeah.
Why is the domain of the function finite?
Why is the domain finite? Because remember, x and was d cross h cross t, and d and h and t are all finite. Okay, by assumption. Okay, so well, so again, this is what I was. If my clicker worked, I would have said this more efficiently. Need a new battery, I guess. The highest point in the lattice is just the pair where again, depends which order you use. I can order it either way, but where, in this case, where the doctors start without any offers and the hospitals start thinking everything's available. I just described it to you in the reverse way, but either way works. And then what happens is by iterated applications, at the first application, in this case, this is a hospital offering, the hospitals reject all but their most preferred acceptable contract. That is, they think they can get anything, so they think they're getting their best contracts. So the next pair of contracts that at the next iteration and now include some offers for the doctors. Then at the second, is sort of F squared is really a Gale-Shapley step. At the next step, what happens is that the doctors reject all but their most preferred acceptable contract from among those that are offered, and that reduces the set of opportunities available to the hospitals. And we go back and forth like that. So essentially, F squared is a step in the Gale-Shapley algorithm, the way this is constructed.
Well, what's the relation between these and, for instance, assignment games which are modeled by it's a two-sided market. You take pairs and you have either whisk transfer, but set of utility vectors for the two individuals. Can I think about it as a discrete version of an assignment game?
You can. I really don't want to go that way now because the discreteness adds when you add indifferences, you have to be a little bit careful. So I'm going to whiff on the details of that, but yes, in essence, the answer is yes.
So here the set of contracts is discrete.
Yes. So the extremal fixed points are obviously doctor best and hospital best because the extremal fixed points are the points where the doctors have the largest set of offers from which they're choosing, and that's got to be best for them. And the hospitals have the smallest set of offers from which they're choosing. That's got to be worst for them. Okay, similarly, in a competitive model with substitutes, there is, if you take a look at a quasi-linear model, for example, with goods that are gross substitutes, you'll find that there is a seller best point and a buyer best point. The seller best point is just the market clearing prices that are highest in every component, and the buyer best point is just the competitive equilibrium point that's where the prices are lowest in every component. Okay, so that structure is also found in competitive equilibrium, and there Yal's point. So it turns out there you have to go to the continuous model to prove that rigorously, but this is the same thing that's going on here. Okay, and notice that so what I want you to notice now as we push beyond, so far this is really close to what you've seen already. Okay, and I want to push a little bit past what you've seen already now. And I want to do that by having you notice that it's as if, in this model, it's as if the, let's say in the doctor offering algorithm, that the hospital could always go back. Eric makes an offer to Ken, and Ken rejects you today, Eric, but later he gets an offer from Shmuel, and how do we know that he won't want to come back and take you? And well, in this algorithm, the algorithm is set up the way I've defined it, that that Ken sees himself as choosing from the set that still includes Eric in addition to including Shmuel. Okay, but because of monotonicity of rejection, because of the isotonicity of the rejection function, he never wants to go back. But it's as if the offers were cumulative. Okay, now that's going to turn out to be important. All right, so we'll come back to that in a little while. The reason we're going to come back to it is that when we do certain package auctions, so why is it a problem that why would it be a problem that Ken can come back and take Eric? Well, in the ordinary matching, it's a problem because Eric might have made an offer to me or something in between, and I might have said, yeah, I'd like to take that, and I'm going to reject, Scott or something sorry, Scott. Along the way, I've rejected Scott, and now all of a sudden Ken wants to come back and take Eric, and that screws up everything, right? So that's what can happen in the matching model. But imagine we have an auction model where we've got only one seller, okay? Then it's not a problem that that Ken might want to go back. And the idea that the offers are cumulative is not a problem when we have only one player on one side of the market, okay? That's going to turn out to be important when we get into the auction applications. So this very same algorithm is going to work for auctions when one side of the market is the auctioneer and has just one participant. Yeah.
Secondly, we have algorithm that can give you doctor or hospital to a stable matching.
Mm-hmm.
Is there any way to reach the stable matching between the two from starting?
So the answers to that are the same as what other people have given you. That would be a different than the Tarski algorithm. And so I don't have anything new to say about that. All I'm trying to do here is to unify in a way that's going to give us some generalizations too. But I'm not addressing the algorithmic question here. Also, this formalization captures the intuition. I would argue for you this formalization captures the intuition we all have about what's going on in matching. Doctors are getting, in the doctor offering, they're getting worse and worse off. The hospitals are getting better and better off. That's where the convergence is coming from. The lattice structure is the mathematical formulation that captures all that. In the Kelso-Crawford algorithm, the wages are going up, the workers are getting better off, the hospitals are getting worse off. This is the mathematical structure that we are looking at. Okay, so let's talk about incentives a little bit. And in order to talk about incentives, the next piece I need is, this was introduced in this paper, the law of aggregate demand. So we have, for any individual f, we'll say that that f satisfies the law of aggregate demand if given any two choice sets, where one's a subset of the other. They're both sets of contracts. If the number of elements that I choose out of the smaller set is no more than the number that I choose out of the larger set. Okay, so this is something like, something about one-for-one substitution, that it's never the case that, somebody comes along and is so good that I drop two other people to take him. Okay, that's the law of aggregate demand. And in a price theoretic version of this problem, what this would be, the reason I gave it this name is that in a price theoretic version of the problem, this means that if you lower the wages that you are paying for workers, you hire more workers. Okay, so it's sort of like a law of demand, but it's an aggregate. It's the workers are not homogeneous, so I'm counting them as if they were a quantity. And that aggregate demand goes up when the wages go down. Okay, the definition requires that when a firm is faced with lower wages, it should hire more workers. Okay, so we come to the rural hospitals theorem. If each participant regards contracts as substitutes and its preferences satisfy the law of aggregate demand, then each signs the same number of contracts at every stable allocation. And you know what? I have a proof on here, but you've seen this twice already, I think, so I think I'm going to skip this proof too. this is exactly the structure you need to do exactly the proofs that you've already seen. So we'll just skip it. Okay. And then we also get an extension of the dominant strategy theorems that you've heard before. This is from our paper, again, the Matching with Contracts paper. And we find that suppose that each doctor can sign only one contract. By the way, the other theorems didn't have that assumption in it. It was many-to-many matching. So suppose that each doctor can sign only one contract, and each hospital reports preferences that satisfy the law of aggregate demand and regards the contracts as substitutes. Then, if you take a look at the one-sided game where just the doctors are reporting, it's strategy proof. In other words, it's strategy proof for doctors, this mechanism. And truth-telling is always optimal for doctors, no matter what the hospitals report. Okay? And so this is obviously a generalization of exactly the same theorem that you saw before. I am going to do this proof because I like my proof better than the other proofs. So so my proof is one slide and goes like this. The proof proceeds by showing that if any doctor D reports any preference P that leads to some outcome X, then each of the following variations leads to a weakly better outcome than the previous one. So we're just going to go from whatever was reporting step by step to truthful reporting and show that the doctor is better off at every step. And actually, this is pretty similar to one of the proofs that you saw. So we start by he reports preferences P, which leads to some set of stable allocations A, including the contract X for this doctor D. Then at the next step, what this doctor can do is he can report that X is the only acceptable contract. And as you've seen, this means that fewer allocations are blocked. So the set of contracts A is still unblocked. And by the law of aggregate demand, D has to be, essentially by the rural hospitals theorem, D has to be assigned at every stable allocation, so it must be, it must get this particular contract X. Report that contracts that are truly worse than X are unacceptable, but otherwise report preferences truthfully. This is the truncation strategy where you say, here's my real preferences, but I'm going to truncate them at X. And if things were unblocked before, they're still unblocked. If you go through the algorithm by isotonicity, the highest stable set is at least as good for the doctors as A. All that can happen when I go through the algorithm is I end up with some points that are above A. So D has to do at least as well. And then finally, report preferences truthfully. This doesn't change anything because if A was unblocked before, it's still unblocked. So if it was stable before, it's still stable. And everything that was better than it, if it was doctor best before, it's still doctor best. So by this sequence of steps, you can go from whatever you were reporting to reporting truthfully and do better at every iteration. This is a lot like the one of the proofs we've seen before. I think maybe, did you show a proof like this, Scott? I saw something a little bit like this being shown. But this, you just go through a series of steps and you do better at each step. Okay, what am I doing on time? It's 10:30 and I'm supposed to finish at 11. Huh?
Not quite 10.
What's that?
10:25.
10 to, oh, we're using that clock. I see. Okay. All right. All right. So, John Hatfield and Scott have a further improvement of this that says, suppose each doctor can sign only one contract and each hospital satisfies the law of aggregate demand and that contracts are substitutes. Then in the reporting game among doctors, that's weakly group strategy proof. That is, there's no coalition of doctors that can deviate in a way that's strictly beneficial to all of them. Have you said anything about this yet?
No, but I should also clarify the citation. I'm not on this one. This is Fukito Kojima.
Did I say?
You said Hatfield and me.
Oh, sorry.
Sorry.
Sorry. Okay.
Get one extra.
Okay.
Credit.
There we go. So yes, I mixed up my K's, I guess. All right. So this is this is weakly group strategy proof, which is a nice property, and we're going to see a property like this again tomorrow for auctions, where it's an especially nice property. So it means that the even if the doctors got together and coordinated, they couldn't deviate in a way that was strictly beneficial for all of them. And should I do the proof? I'm trying to think. Maybe I won't do the proof of this one. Because I'm going to come back. I think I'm going to skip the proof of this one because I'm going to do group strategy proofness tomorrow. And instead, I want to push on to, I want to take a breath and push the cumulative offer processes. Yeah, Eric.
Can you say anything useful about strategy proofness when doctors are attending more than one contract?
No. No, can't. The right. So the
or
you know,
additional restrictions with simple restrictions which are headed for.
yeah. You know what? You just gave me a research idea. Let's talk about it after break, okay? So there might be a result from auction theory that's adaptable, but I'm not going to attempt it standing here on the. I'm not going to attempt it standing here. Okay. So what I will attempt standing here is so a little while ago I told you. Suppose we were doing this Gale-Shapley. Oh, you guys look tired out there. I don't know. Am I going too fast? I'm not quite sure. So I told you that when we were looking at this cumulative offer process, that the reason substitutes was important is that, you know, when Ken turned down Eric, if he wants to come back and take him later on, that's a big problem if Eric's already made an offer to somebody else. So so that would be a problem for matching. So a variation of the deferred acceptance algorithm in which hospitals could go back, that's not a problem when contracts are substitutes because the rejection function is isotone. So once an offer is rejected, it stays rejected. So that means that the Gale-Shapley algorithm is equivalent to one in which one can go back and take any offer that she's ever received. Okay? If hospitals don't regard contracts as substitutes, just to summarize, it's no longer true that the fixed points are stable. If you remember, the argument that fixed points were stable said, well, you know, it says you'd reject a contract if it was one contract, but what if there was a bunch of contracts that were offered to you? You had to still want to reject it. So it's no longer true that fixed points of F are stable. The deferred acceptance algorithm may fail to terminate in a stable match. And the contracts that emerge from the cumulative offer algorithm may even be infeasible, in which Eric ends up being assigned to multiple hospitals, okay, if you just terminate in this way. So everything comes crashing down if you try to do cumulative offers without substitutes, okay? But if there's just one hospital, if we think of this as an auction, then the final match will always be feasible, so we don't have the feasibility problem. So I want you now to imagine, I want to begin to connect this to auction theory. I want you to imagine that the doctors are bidders who are interested, for example, in supplying a package of services to an auctioneer, which may include various services on various terms at various prices. Okay, so it's, you know, rich enough model. And the auction works like this. The bidders support, remember, we're still in the finite world. There's a finite set of prices, a finite set of terms. So the bidders submit a rank order list of their contracts. Here's the contract I'd most like to sign. Here's second, here's third, and so on. And the auctioneer submits a rank order list of collections of contracts. That's his preference function. And we run a cumulative offer algorithm that works like this. Each bidder that's not in the currently winning package, so if Ken's the auctioneer, he's holding some set of contracts. Eric's contract has been rejected, so Eric makes a new offer to Ken. Maybe he offers him a lower price. The auctioneer tentatively rejects all the contracts except its most preferred combination, which can include at most one bid from each bidder. Now, by the way, what it used to be, I've sort of abandoned this language. I've sort of gone with the world and using the language deferred acceptance, which I've always thought was rather misleading because the point of the algorithm is not just that you accept what's there at the end. The point of the algorithm is that the rejections are permanent, right? In the ordinary algorithm, I would have called it, if I were naming it 50 years ago, I would have called it the greedy rejection algorithm, right? Because what goes on in that algorithm is that at every round, it's a greedy algorithm in which at every round you take the best stuff and you throw the other stuff away, never to look at it again. Okay? That's what the deferred acceptance algorithm is, and you'll see we're going to use that conception of it later. Cumulative offer is different. It doesn't greedily reject. It holds on to some of the old offers. So Ken here can regard some of these contracts as substitutes, and he can go back, and it's no problem if there's only one auctioneer. Okay, so theorem, the outcome of this cumulative offer process is a core allocation. So this is very closely related to stability. And let me prove this for you. It's pretty easy. This is also an NTU proof, by the way. That is, matching theory is virtually all of matching theory does not use transferable utility. There's no money that it doesn't have to be that there's quasi-linear utility. There's no quasi-linear utility in this model either. It's a matching theoretic type model. So what happens here? At the end of the auction, each bidder has made every offer that it prefers to its final outcome. It's a matching theory kind of argument. I've gone down my list, and whatever's been selected at the end, everything that I like better has been offered. So any blocking coalition has to, if it's going to make the people better off that participate, it has to include offers that they've already made. So a matching theory argument that Al could very well have made at some point, right? The auctioneer has accepted the combination of accumulated bids that it most prefers. So there can't be any collection of offers from that have already been made that the auctioneer likes better. So any collection of contracts that you propose is either worse for the auctioneer or it's worse for one of the bidders. So it's unblocked, and that's the proof. Okay, it's real simple. So you can take this to auction theory and get a core allocation out of a cumulative offer process. Yeah?
So that is in the call with respect to the reported preferences, right?
Yes, this is just the with respect to report. Now I will show you incentives in a moment.
Is there any?
Yeah, we're going to come to incentives next. Okay, this is an algorithm property rather than an incentive property. Yeah.
Are the offers made in rounds?
Yeah, this is just like the deferred acceptance algorithm. You put in a list, and the computer runs
Yes,
through.
but it's made in rounds.
The algorithm runs in rounds.
Yes. So the auctioneer doesn't know in advance all the offers by all the bidders.
No, that's right.
And that allows them to go down step by step.
Yes. Yeah. So you want to think of this as a sealed bid auction.
Yes.
There's just like it's analogous to a matching process. What I'm trying to do is do something unifying here. So the notion is, again, this is supposed to look a lot like a matching model. We've just put down a list of bids and run an algorithm that looks a lot like a deferred acceptance algorithm, except that there can be complements. And even with so one of the things here, so we've asked about complements before. One of the things here is that even with complements, we're still getting a core allocation, right? So that's new in this compared to what you get in matching theory. Now the reason we can do that here is that in matching theory, the problem with couples, for example, which is complements, is that you accept one couple, somebody else all of a sudden gets a job in another city, and the other member of the couple no longer wants to work in Chicago because the spouse is working in New York. So when you have complements, you might have to move back up the list and say, oh well, gee, if I can't get her anymore, then I want him instead. But I'd already rejected him because I thought I had her, and the algorithm doesn't work anymore. But in the auction case, we don't have that problem with a single auctioneer. So the backtracking is not a problem. The logic that tells you that it's stable, that is that it's a core allocation, still survives. Okay, so we get a core allocation this way.
At the end of each round,
Mm-hmm.
every bidder knows what everybody else bid.
No, this is not rounds for bidders. This is rounds of an algorithm. It's a sealed bid auction.
Oh, I see.
It works just like a matching.
Yes, I
Okay. Okay. So, moreover, if the auctioneer regards contracts as substitutes, then the outcome of this auction is also the bidder best core allocation. Okay. So this also sounds a lot like so when it substitutes the auctioneer never backs up. Once an offer's been rejected, it stays rejected, and anything that the bidders like better is blocked. Okay, this is actually a corollary of the matching theory result, because in the substitutes case, as I've already shown you, this algorithm coincides with the Gale-Shapley algorithm. Or if you ran the Gale-Shapley algorithm, this is what you'd get, because you wouldn't, you wouldn't back up in this algorithm. You get exactly the same thing. So this is really a corollary of the Gale-Shapley algorithm result. Okay, let's take a breath. Okay, so I'm now going to add some cardinal structure, which is what we usually do in auction theory. I want to get Vickrey auctions into the package, and Vickrey auctions are inherently cardinal. Okay, we need the payments. We have additive separable payments, and I want to show you that once we've specialized the structure so that I can look at the intersection of the Vickrey auctions and Gale-Shapley algorithms, the dominant strategy theorem is the same theorem. Okay, so that's what I want to show you. So what I need to do is put in quasi-linear utility. And I'm a little bit frightened here, I must imagine. I have to tell you, because I don't know what math background everybody has, so I have to do a little bit of math review. But I have to do this for you, Scott, because there's a proof we've been talking about. That you just need this math to do this proof. So we're going to do a little bit of math, and then we're going to do a proof which I absolutely love, and I have to show Scott, so you guys have to sit through it. Okay, here we go. Okay, so we're going to talk about submodular minimization as a little background. So actually, we actually did do submodularity generally. This slide is a little bit too old. I'm going to remind you, this is the general definition of submodularity. Given a lattice X with a partial order there, a function is called submodular if for all 2 points in the lattice, when you evaluate the function at X and you evaluate it at Y, you get at least as much as when you evaluate it at the meet plus evaluating it at the join. This is the general way of describing the idea that that if you have several variables and if you increase some variables, you reduce the marginal return to other variables. This is an abstract way of capturing that inequality. Okay? The way if you want to see this offline, you reorganize this as f of the join minus f of x is less than or equal to f of y minus f of the meet. And you'll see that that tells you that the marginal return to increasing certain variables goes down when you've raised the other variables. Okay. For a smooth function, it's submodular if and only if its mixed partial derivatives are non-positive, which is another way of saying, again, the marginal returns fall when you increase the other variables. Okay, and again, the indirect utility function, I remind you, is, or Fenchel dual, or call it what you like, is pi of p, is you have a bidder that maximizes how much value it gets when it has to pay prices p for the inputs that it is buying. By Hotelling's lemma, again, the bidder's demand for good L at prices p is just minus the partial derivative of this indirect utility function with respect to L, where the second term, the subscript, denotes a partial derivative. Goods are substitutes if and only if pi is submodular, that is, if and only if the demand for good L is non-decreasing in the price of each other good. Okay, so these are things we've already said that I'm reminding you of. Okay. Now, if there are multiple copies, so I'm going to live in a world that might be discrete. By the way, this theory is going to apply both to divisible and indivisible goods. But keep in mind, for concreteness, let's keep in mind the discrete case. And suppose that there might be multiple copies of each good. So market clearing prices might fail to exist. We already know that from Kelso-Crawford that if we have one copy of each good, if we have different workers and they have wages, market clearing prices do exist. Right? Basically, they have a constructive algorithm for finding them, at least approximately. But if there are multiple copies, market prices could fail to exist if a small increase in the price of a good can lead either to the bidder reducing the demand for the good by 2 units. So suppose that there's some good, that I want either 0 or 2 of. Now the substitutes condition obviously holds because there's only one kind of good. But my demand jumps from 0 to 2. If the supply is 1, I can't clear the market. Or the bidder might reduce demand by 1 unit, but then substitute 2 units of another product, and that could also cause non-existence. So in another paper with Bruno Strulovici, we made the definition that goods are strong substitutes. If when were you to treat each unit separately, the redefined goods would be substitutes. That rules out these 2 cases. It basically, in the redefined model, we're back in the Kelso-Crawford world where we know that market clearing prices exist. And for the 2 goods that are identical, they're going to end up with identical prices. So we'll have found market clearing prices for the whole market. Okay? So Kelso-Crawford then implies that with strong substitutes, market clearing prices exist. Okay, now I want to come to Vickrey auctions. Oops. Well, Goost. If the Goost are strong substitutes for all bidders, and if the auctioneer has a fixed supply to sell, then the Vickrey auction outcome is the bidder best core allocation. Okay? A Vickrey auction outcome is the bidder best core allocation. We start to see where the incentives are coming from, right? This starts to the Vickrey auction and the bidder optimal core allocation, the doctor optimal core allocation start to come together. So again, what does this mean? It means that in the Vickrey outcome, each bidder gets its highest payoff in the core, and that the seller gets its lowest revenue of any point in the core. So if it's bidder optimal, it's got to be seller pessimal in the core. And this result is going to connect incentives in matching theory to those in ascending auctions. Okay? Okay, so let's prove this theorem is not hard to prove. So, well, maybe. Let V be the coalitional value function that's constructed from the data with 0 value to coalitions that exclude the auctioneer. And so what has to be true? If you take any payoff to bidder J that is higher than Vn minus J. So this is, take a look at what the coalition of everybody is. I'm looking at Eric. Eric is player J. Take a look at what everybody can get without Eric and then what they can get with Eric. And suppose his contribution is 10. If he tried to get a profit of more than 10 in this auction, that would be blocked by the coalition N minus J because they don't need him. They don't have to give him 11 to get their total. They could just, they'd do better on their own. So we know that the most Eric can get at any point in the core is Vn minus J. But Vn minus J is his marginal contribution to the coalition of the whole, and that is the Vickrey payoff. So I actually don't have a slide that says this, but those of you who know the Vickrey auction, your payoff is your marginal contribution to the coalition of the whole. Let me give you an example. In a second price auction, if there's something that's worth 15 to Eric and it's worth 10 to Ken, who's the second highest bidder, then in a second price auction, Eric pays 10, and his profit is 5, and 5 is the amount of value he brought, right? If he weren't there, the auctioneer and Ken together could have had a total payoff of 10, and with him there, they have a total payoff of 15. The total value is 5, and he's being paid his marginal contribution. Well-known property of Vickrey auctions. So it can't be that at any point in the core he's getting more than that, because if he were getting more than that, we'd say, screw it. We'll do it without him, and the complementary coalition would block. So suppose that, as we're going to show later, for the case of substitutes, that V is a submodular function. We're going to show the coalition value function is submodular. Consider any coalition S that includes the seller, and let it, for example, be 0 dot 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 1 dot 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 k, then I claim that S is not a blocking coalition. So I have to show you that if V is submodular, that the Vickrey outcome is in the core. It's going to be the best in the core because nobody can do better than this. And I just have to show you that it is in the core. And here's how I show you that it is in the core. I'm going to make sure that the total payoff to the players in S is at least what they could get on their own. That's what I have to show you. So there's the total payoff to the players in S. What is it? It's equal to the total payoff to the players in S, since the Vickrey outcome is efficient, is equal to the total payoff to everybody minus the total payoff to the players not in S. And the players not in S are getting their Vickrey payoffs, which are pi j is Vn minus j. And Vn minus j by submodularity, this is the marginal contribution that you're making to a big coalition. Let's take a look at your marginal contribution to a smaller coalition. And I'm going to set this up to telescope so that what I'm going to do is I'm going to put in here terms that is player k plus is 1's contribution to everybody except S, and then player k plus 2's contribution to that coalition plus k plus 1, and so on. So I'm going to get a telescoping sequence here. And each of these terms is bigger than each of those terms by submodularity, because this is the biggest coalition. You make the smallest marginal contribution. So you make a larger marginal contribution here. So I'm subtracting bigger numbers. So I get a lower total. And then I sum the telescoping series. And what I have left is Vs. OK? So, so I've shown you that the payoff to the members of coalition S is no more than Vs. Right, so this proves that that in the substitute's case, if the coalition value function is submodular, which I haven't proved for you yet, then the Vickrey outcome is the bidder best core allocation. And the bidder best core is where the incentives are coming from. In matching theory, you can do that too. So to finish this, and this is in the last 10 minutes, and this is what I've been building up to and promising to. This is a new proof, by the way, that's never been published anywhere, and it's the old proofs of this were horrendous, right? So this is for put on your math cap, because this is about I love this proof, so I have to do this for you guys. Okay, so what I've got to do is I've got to prove for you that this function v is submodular, but the hypothesis we have is that the goods are substitutes. So we got a function of goods that satisfies some inequalities, and we have to prove that a function of bidders satisfies some inequalities. So how do we get from goods to bidders? Right? That's the hard part of this proof. So we have to use we're going to use our hypothesis that indirect utility. We're going to characterize substitutes in terms of indirect utility, which is a function of prices. That function is submodular, and from this function of prices being submodular, we have to prove that a function of bidders is submodular. So how are we going to do that? Okay, so we have to derive the conclusion that this function of the set of bidders is submodular. So here's the lemma that we're trying to prove. Suppose that for every bidder, preferences are quasi-linear and goods are substitutes, then this function, a function of the set of bidders where we maximize allocating over the bidders a fixed supply of goods, is submodular. Okay, that's what we're trying to show. Okay, and this is the proof. Okay, so I need an aside for you. Theorem of Tapas. Those of you who know me know that you hear theorems of Tapas a lot. So here's a theorem of Tapas. Suppose that I have a product lattice x cross y with an order, and I have a function from x cross y to r that's submodular, and then I minimize over some of the arguments. The resulting function, the minimum, which is a function of y, is submodular. This is very much like if you had f of x and y, if this were a convex function and you minimize this over y, the resulting function of x would be convex. It's actually almost the same proof. If you know how to prove the one, you know how to prove the other. It's almost the same argument. Okay, so this is what I'm going to use. I'm going to show that I have some function that's jointly submodular as a function of prices and bidders, and then I'm going to minimize over the prices to get the coalitional value function. So here's what the function is. I'm going to look at this function, which is the sum of the indirect profit function for the bidders in J plus P dot X bar. This is a function of jointly of P and S. Okay, the indirect utility functions are submodular, and we have to show that F is submodular. And how do we know that F is submodular? Well, this turns out to be a legitimate way to check this, but I will check it for you this way. I'll let you convince yourself that this is actually a proof. If you look at variations in S alone, you ask yourself, suppose that I were to add bidder I, and ask yourself, what's the marginal contribution when I add bidder I? Well, you observe if I add another bidder here, it just adds another term here. It's additively separable. And additively separable functions are submodular trivially. That's uninteresting. Suppose that I looked at this as a function of P alone, holding the set of bidders constant. Well, this is a sum of submodular functions, and the sum of submodular functions is submodular. So it's submodular in P alone. Now let's look at P and S together, and I can vary either one and then vary the other one. So suppose I add a player to S, and I take a look at the marginal contribution. This is a non-increasing function of P. Why is it a non-increasing function of P? Because indirect profit functions are non-increasing. When you raise prices, the consumer's worse off. Okay? So these three things together imply that this function is submodular. So here's how the lemma goes. We're going to calculate the coalitional value. There it is. We're going to use the fact that a market clearing price exists to write this as to write the dual formulation of it. So we know that for any positive prices P and any feasible allocation here, this is less than that. And if we find market clearing prices, this term is 0, so these things will be equal. So this is just the usual argument for duality, but applied to a discrete world. If market clearing prices exist, then duality holds. And now what we're going to do is we're going to group terms. I'm going to take the Vj xj and minus P dot xj, and I'm going to group them together. And I'm going to move the maximum. This all becomes additively separable. And this thing, of course, is just the indirect utility function for j. So I've turned this now into the minimum over P of the sum of pi j of P plus P dot x bar. But that was our function f. So I've characterized the coalitional value function as being the minimum of a submodular function of P and f with respect to one of its arguments. And that proves that it's submodular in the other argument. So if the goods are substitutes, so this is a new argument, right? Much shorter than any previous argument for this, if you've ever looked. If the goods are strong substitutes, then V is submodular, and so the Vickrey outcome has the properties that I've described. Okay. So let me do a summary and sort of a forecast. So what was I trying to do today? So the matching with contracts approach is supposed to be unifying. It's supposed to expose strong links between matching theory and both price theory and auction theory. Okay, that these concepts are that when Gale and Shapley first did it, looked completely idiosyncratic and looked like they had nothing to do with the way we approach things in standard economics. Through the matching with contracts approach, we find a strong common core that a lot of it shares. And the submodular dual representation works in both, and we can begin to prove theorems and find analogies that run across both price theoretic models and matching models. The extended substitutes condition plays a key role in all three. It's used for stable matches to exist and the Gale-Shapley algorithm to work. It leads, as Arrow and Hurwitz showed, Taton-Moss stability, and it leads to the existence of seller best and buyer best equilibria in quasi-linear models. Vickrey outcomes lie in the core and result from cumulative offer algorithms when you formulate things this way. And in the next lecture, which is tomorrow, I'm going to expose more connections, including a deeper connection to Marshallian dynamics. And it's going to turn out that that connection to our Marshallian dynamics, so just a quick introduction for tomorrow. I'm going to be talking about the most complex auction in history that we are designing for the U.S. It's huge. It's called the incentive auction. It's what we will be doing. What the U.S. government will be. I'm leading the consulting team that's doing this design. It's $55 billion in transactions according to the Congressional Budget Office. We are attempting to buy television broadcast rights from television broadcasters to move the broadcasters that stay on the air into a smaller set of channels and the lower numbered channels in the UHF band, and then to create mobile broadband licenses out of the upper channels and to sell those to mobile broadband companies like AT&T and Verizon, T-Mobile, Sprint, rural telephone companies, and so on. And it turns out that the technical complexities of that auction are extraordinary. And you'll see about them tomorrow. And this theory that we've been talking about, the auction design that we're using is called a deferred acceptance auction. We are using this larger view that we have managed to create by understanding the connection between auctions and matching to invent a new kind of auction that will be applied to this problem. And tomorrow I will tell you about its many properties and why we're doing things that way. But the big advantage of unification is that it leads to new insights. You start to see things that appeared to be very different as being versions of the same thing. You start to see the couples problem showing up in markets. That's what unification is all about, and that's the reason to approach this whole subject from the point of view of lattice theory. So I think that's all I've got for now. What's that?
The last lemon you showed, it's really very nice.
Thank you.